Hi everyone. So in this video we introduced Nesterov momentum, which is it turns out to be a very successful momentum algorithm that's typically used in commonly used in deep learning or for training deep neural network architectures. So this is actually a theoretically well-founded algorithm that has well-formulated convergence rate guarantees, and basically the guarantees on the excess error, as we'll explain. So the idea behind Nesterov momentum is very simple, right? So the idea behind momentum is that I use this update, right? So the alpha v minus epsilon g, where v is an accumulation of past gradients, right? So v is basically every time I multiply by alpha, so it's an exponentially decaying moving average of past gradients. And what Nesterov momentum does is that before it computes the gradient, it exploits the fact that we already know the alpha v, right? So before making the update, right? So you can think of this update to the theta as theta plus alpha v minus epsilon g. The part that is the alpha v, I already know that from the previous iterations, right? And it doesn't depend on the loss function. It doesn't depend on the computation of the gradient, right? So I incorporate that term before computing my gradient, right? So in a lot of the literature, this alpha v term here is called the look ahead term, right? And the idea is that we look ahead to how the parameter update will be computed, right? And we incorporate the term that captures the information about the past gradients in the parameter update before computing the gradient. So the gradient is computed based on this theta tilde here, and theta tilde includes the alpha v term, right? So here, this theta plus v, you can also think of it as theta tilde minus epsilon g, right? So after updating the theta to theta tilde, it looks like stochastic gradient descent. You compute the gradient, and then you update your parameter as theta tilde minus epsilon times the gradient in the negative gradient direction with a step corresponding to the learning rate, right? So really this is the difference between the classical momentum and Nesterov momentum, is this look ahead term. We incorporate the part that reflects the past gradients in the parameter update before computing the gradient. And then we compute that gradient based on theta tilde, not the theta, based on the updated parameters with the alpha v term. Now the advantage is that there is actually a theoretical proof that the excess error with a convex coast is order 1 over k squared, even if we are not using many batches. So even without many batches or without the stochastic aspect of gradient descent. And remember that SGD had only linear with a strongly convex coast. It can only have a linear order 1 over k, a linear decay of the excess error. And remember, the excess error is basically the training error that is added from not finding the optimal solution. So it's the training error of the current solution, of that solution that's found at the kth training iteration, minus the training error, the best training error that you can get with across all the parameter space. So let's remember something that we said before. So we said before that there is something called the Cramér-Rao bound, right, which is a fundamental limit in estimation, and that limit says that the generalization error, not the training error, cannot decay faster than linear, right? So we said that maybe anything that decays, there is a paper in like probably 2008 in NIPS that argued that that if you go any faster, you're doing than linear, then you're doing overfitting. Then why is Nesterov momentum that's successful in deep learning. Now that's related to another comment that we mentioned before, which is with very large data sets, right? And you can see it earlier in the notes. The concern is really about underfitting, not overfitting, right? So that's why this fast, and we also said another comment that it's really the fast exploration, the fast initial exploration of the parameter space is what gives SGD its advantage with very large data sets. So because deep learning involves very complex models with a large number of parameters and typically large data sets as well, so making fast progress sometimes in many practical settings is the overwhelming dominant factor. And that's why making progress even faster than the best speed at which you can improve the generalization error, fitting fast to the training data can be very important. And maybe that's a reason of why Nesterov momentum is that successful in deep learning. Thank you.